Good morning, everybody. I, Chaitra UR, Assistant Professor, Department of Electronics and Communication Engineering, St. Joseph Engineering College, welcome you all to the webinar on Automated Detection and Quantification of Parasite-Infected Blood Cells, hosted by the Electronics and Communication Engineering Department in association with SJEC Matlab. In the panel, we have the speaker for today, Mr. Amith Kamath, Dr. Dayakshini, HOD ENC, Ms. Nandini Maninarayana and Ms. Shama BN, Assistant Professors, Department of ENC. I now request HOD Dr. Dayakshini to welcome the audience and the speaker.
Good morning, all. Parasitic diseases present many problems for global health. They cause a wide spectrum of hematologic abnormalities, particularly malaria, diagnosis of anemia, cytopenia, eosinophilia, etc. Diagnosis for these diseases require manual counting of parasites in infected red blood cells by a trained microscopist. Accurate parasite counts are essential to detect and treat the diseases. They are also important for testing for drug resistance, measuring drug effectiveness, and classifying disease severity. However, microscopic diagnostics is not standardized and depends heavily on the experience and skill of the microscopist. At low resource settings, it is difficult for the microscopists to maintain their skills and diagnostic quality. This leads to incorrect diagnosis. So development of automated detection systems for parasitic diseases using image processing and machine learning approaches are very much essential for accurate detection and diagnosis. So today's webinar on automated detection and quantification of parasite-infected blood cells by Mr. Amith Kamath, member of academic team MathWorks India, will provide insights on this research area. On behalf of management and staff of St. Joseph Engineering College, Mangaluru, I welcome you, sir, for this webinar. A cordial welcome to my colleagues, Ms. Nandini Maninarayana, Coordinator, SJEC Matlab, Ms. Shama BN, Assistant Professor, ECE Department and Coordinator of today's webinar, and Ms. Chaitra UR, Moderator of this webinar. Welcome, madams. A warm welcome to all participants. This webinar will provide some insights to carry out research in automated detection of parasitic diseases. Thank you.
Thank you, ma'am. We welcome you too. I now request Ms. Nandini Maninarayana to introduce the speaker.
Good morning, all. It is indeed my pleasure to introduce today's speakers, Mr. Amith Kamath. Mr. Amith Kamath is an education technical evangelist at MathWorks and is based in Bangalore. Mr. Amith works with the academic institutes in India on the adoption of MathWorks workflows in curriculum and research. Mr. Amith has been with the MathWorks for the last 7 years and had previously worked with the Engineering Development Group and software development in the image processing and computer vision areas, focusing on workflows for image registration and pixel labeling. His area of interest includes computer vision and software engineering. Mr. Amith Kamath has a bachelor's degree in electrical engineering from NITK Surathkal and a master's degree in electrical engineering from the University of Minnesota, USA. Thank you, sir.
Before we start the session, there are some instructions for the participants. Mics of the participants have been muted. Any queries, please feel free to post it in the chat box. E-certificates will be provided to the participants who actively participate and fill the feedback forms. Link for the feedback will be posted in the chat box at the end of the session. Recording of the webinar will be available in SJAC YouTube channel in a short time. Now, I request the speaker to take over. Over to you, sir.
Thank you very much. This is Amith for the introduction as well as for setting this up so professionally and so well organized. I really appreciate this. So I believe I'm being transferred the presenter rights and that's happening. So let me quickly share my screen and then bring up my presentation. So I'll be talking for the next 1 hour, so hopefully you get used to my voice. It's not too loud and it's not too feeble. If the audio or video for whatever reason is not clear, please do post in the chat window. I'll try to keep track of it and adjust accordingly. Okay. So I have the chat window open as well, so that's all set. I really have only 3 slides today, so in terms of slides, it's going to be very light. But I'm going to show you a bunch of things on MATLAB, and then I'll be happy to share this with you later on as well. To if you'd want to try to run this on your own too, right? So very briefly, in terms of the agenda or the plan for the next 1 hour, we'll be really doing 3 tasks, okay, based on the topic that we mentioned earlier. And we'll go through several user interfaces or applications which help you do these tasks more easily, right? So we are going to look at some cell image slides and then access and visualize the data. We're then going to do some rapid prototyping, which is really what's important to really get your hands dirty with the data, right? We'll run through some very well understood and standard image processing methods in task 2. And after that, we'll try to show you how you can automate this, meaning, all of this, you sort of do it one at a time, and it may be time consuming for doing this for several images, and we'll try to show you how you can do this for multiple images altogether, right? Finally, we'll then sort of revisit this algorithm development for image analysis, and we'll try to improve these methods using a couple of other specific algorithms. Okay, we'll then account for the quality, variability, and so on of the images that you have in your data set, and then we'll finally try to put together this automated version of the algorithm at the end. I'd appreciate it if you could, try to make this interactive, both for my sake and for yours. And, during the presentation, please do ask questions in the chat panel. I'll periodically check for anything I can answer. And, after the presentation, if you have questions later on that you couldn't ask during this period of time, please do. I'll share my email address, and please do reach out to me, and I'll be happy to help you later on as well. Okay, that's about it really in terms of slides. I'll jump directly into MATLAB. So I am not entirely aware of how familiar all of you are with the MATLAB interface. So I may go a little more slowly and spend some time showing you what there is and what is what, right? Really, I want you to be able to try to do this on your own as well later on. And so when you try to do this, I don't want you to be stuck anywhere, right? So I might go a little slower than normal. So please bear with me, and hopefully it'll still be useful for you to pick up. Okay. So this is the MATLAB interface. There is, your listing of your contents of your current folder here on the left-hand side. There's a command window at the bottom here where you can type in commands. And then this is the editor window right here, okay, where you actually write code and write these things called live scripts these days. There's a lot of training for you to do this online and learn more about how these things work on your own. So you know, if you're interested and if you're not already familiar, I'd encourage you to please look through those online courses. There's one particularly called MATLAB on ramp, which is great, and which will cover all of these very basic um, you know, ideas about how these things work, right? What I have here is this thing called a MATLAB project. Okay, so parasitology classification, that's a MATLAB project I have, which is sort of, if you can think about it like it's a package in some way of my live script as well as any supporting code and supporting data that I want. Okay, so it sort of packages all of this together, and it's an easy way to organize your project, right? And that's kind of what I've done here. The advantage also is you can have all of your code on the MATLAB path, and you know, things will be set up in a way that it should just work. Okay, so that's the idea behind this. So don't when I share this with you, don't get scared about all of these different files and what do I do. You just open the .prj file and then the project will open up. Okay, and inside this project is this particular .mlx file. So MLX stands for MATLAB live script or MATLAB executable, live executable, right? MLX. And so, you know, that's the file that I'm opening right here. Okay. So what we're going to attempt to do today from the image processing perspective is, let me zoom in a little so that you can see this more clearly. So we have slide images, and by slide images, I mean images on a pathology kind of slide, right? Which look like this, okay? These are blood cells, and some of them you may notice over here, these two, for example, have these kind of purple patches in it, right? So really what this is this thing called the Babesia parasite, okay? These are thin blood smears, which are on this pathology kind of slide. And our idea is to explore options for developing an automated function to detect the presence of these, okay? So as humans, it's fairly easy for us to say, okay, you know, there are 1, 2, 3, maybe 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. So 16 blood cells here, and there are 2 of them that are infected by this parasite. Okay, so this is a just for your reference, it's a malaria-like parasite, popular in the US, unfortunately. I wouldn't say popular, I'll say common in the US, but also present around the world too. To you know, for the regional context here in Mangalore, I think you know, I'm guessing we could do something similar for malaria as well, but that's something I haven't tried, so I won't talk much more about that, right? So we can do this as humans for, you know, we can say 2 out of 16 cells in this you know, thin blood smear has this parasite. So it's a quantification of the infection, right? Now let's say you have 30 of these images. And so how quickly can you do that, right? So as humans, you'll have to sort of, and let me actually show you at the end what we want to be able to do with all of this, right? So, you know, all of these different slides we have here, right? We want to, as quickly as possible, while being as accurate as possible, we want to try to say, okay, so there are, you know, this percentage of cells in this slide are infected, and 28% of this slide is infected, right? We want to be able to say this as quickly as possible without sacrificing accuracy, right? So that is the whole point of automating this, of using computational techniques like image processing to do this, and to be able to demonstrate to clinicians as well as to you know, patients and other stakeholders that such methods are accurate enough, and they can do a reasonably good job, right? Um, Obviously, these days there's a lot of talk about AI and all of that. Um, the quick thing I'd like to point out there is these methods are not replacements to doctors, not replacements to people who've trained in medical schools for years, right? These are just supporting tools in some way to make their life easier, right? Especially in this COVID situation now that, unfortunately, hospitals get overloaded, and there's so much testing load and so much case load and all of that. That technology in some way, I think, needs to help make people's lives easier, right? All right, so with that kind of a background, hopefully the problem is clear. We want to scale up the detection of these parasites in images like this, okay? So really, we'll go through a bunch of image processing functions or methods that are well known, and I'll try to explain as we go how those things work. Okay, so we'll get started. Just a disclaimer: all of these images are used from the CDC website. CDC is the Center for Disease Control in Atlanta, and all the images there are used from by their permission, right? Okay, so the cool thing with this live script really is we can divide our kind of analysis or code into these sections here, right? So if you notice this blue bar right here and this blue region here, I can click on this blue bar, and whatever code there is in that region, right, within that section runs, right? So what I'm doing here is really just cleaning up everything so that I don't break things, okay? This is just some boilerplate to make sure that the project is open, so that I have all my code and data and everything set up such that things don't break later on, okay? All right, so the first step, which is task 1 to do this, is to actually access and visualize the data, okay? Let me show you how this data looks like outside of MATLAB, okay? So you may come across, or you may have data like this of your own, right? And they may be organized in this kind of a format. So I'm looking at in my Windows Explorer, this folder data, which has subfolders here. There's this one called babesiosis, and then I can look at these images using the Windows image viewer, hopefully, which comes up. Interesting. Looks like it doesn't like my well, that app for whatever reason isn't working. So let me try to, hopefully it's clear here, and I try to zoom in as well. So view preview panel. Okay, I think that's sufficient. So these are my images, right? I have a bunch of different images right here. I think there are 16 images, okay? And they all look similar to some extent, but also slightly different. For example, the background in this one that I have selected here is slightly different than over here, right? The color of the cells here in this one is slightly more, brighter or more saturated than on this one, for example, right? So this one's kind of little like it's kind of whitewashed in some way, right? So there are all of these variations in our data set. And so, we'll have to take that into account, right? It's not just because your algorithm may work on one image does not guarantee that it'll work on the others. So we'll get to that, handling this variability later on, okay? So generally on any kind of project that you're working on, which looks like this, with images, you will have a bunch in your in a folder, right? So to load that into MATLAB, one of the best ways to deal with this is to use this thing called the image data store. Okay. Now, if you want to learn more about what data stores are, you can click on this link right here, and then hopefully the documentation page opens up here, where you can learn more about what it is. Okay. At a very high level, what the purpose of this data store really is that it allows you to manage collections of images, where the entire collection does not necessarily fit in memory. Okay, so in this case we have 16 images, right, and all of them are fairly small. If you notice, it's 5 kilobytes, 9 kilobytes, and so on. So in most modern computers, back in the day, this was probably fairly large, but in most modern computers, 5 kilobytes is really nothing, right? Is peanuts in terms of disk space as well as memory space, right? So that won't be a problem for our circumstance. But let's say you have 16,000 images. Can you load all of them in memory at the same time? Possibly not, right? So in those circumstances, image data store is even more useful, right? In this kind of situation, the utility of creating this kind of a data store is that you can have all of those files listed together, right? It'll tell you where the file location is. It'll tell you, labels. If you want to label this data for machine learning or deep learning applications, you can add labels as well. And I'll show you what this IMDS, essentially this is what it is, right? It's an object with a bunch of properties. I can then look at imds.files, and then you'll see all the locations of the files are available and known to this particular data store. Okay. So data stores are really these objects that can handle working with large sets of data more easily. Okay. And so when I say these are objects, you may have done some object-oriented programming in the past, where you know that these objects have properties or its components and methods or functions, right? So properties are also called sometimes I think they're called sub elements, right? I think in C they're called C++. I think they're called member elements or something of that sort in C++, right? They're called properties in MATLAB, and so you can look at the properties of this data store, image data store particularly, by just saying properties of this. So when I run this, you'll see that these are the properties of this data store, right? Methods or member functions are functions that you can run on this data store, and that's also listed right here, right? So for example, a popular one is to read image, right? So you can say, and we'll use that next over here. You can say, okay, this data store, I'm going to give you an index of the image I want to read, and then I'll call the read image function, and the data store will then go into that particular index and read that image and give that back to me. Okay, so there are these very useful methods to work on this kind of data as well, right? A quick nuance, just so that some of you may be familiar or may be interested. This is, this line here says that it's inherited from handle, right? So in MATLAB, there are two types of classes. There is this thing called the handle class and a value class. Okay, so value classes are, if you're familiar in most object-oriented programming languages, value classes can only be passed around by value, not by reference, right? You can't have pointers in that sense. They are just, you have to pass the entire data when you pass it through functions. Handle any class that inherits from handle is a handle class, meaning they can be passed by reference. So there's only one instance of this in memory, right? And when you pass it around in functions, they're by default passed around as references. So there's no memory, you don't waste memory by creating copies of this, right? It's already memory efficient that it only holds sort of a listing of these files, and it doesn't load it in memory in the first place. But additionally, it's also a handle class. So this so you know, right? Okay. So here's the read image function that I was talking about, or method that I was talking about right here. What you can do is, let's say I choose, and this is also another interesting thing where you can add these interfaces like these sliders, right? So let me choose this one here. So it's the 8th image. I'm going to go to the data store and say, hey, data store, IMNum is 8. Read that 8th image for me and show it here, right? And then I can choose the second image. I can sort of, keep doing this, and it'll return the corresponding image to me. And you can sort of explore how this data set looks like. Okay. So this is an easy way to sort of do this also. At this point in time, I'll also sort of show you the image browser app as well. Okay. So the image browser app, let me try to open it. So this is not working because it looks for IMG set. So I will do image browser and then give it IMDS, right? It's just the variable name is not set up correctly there. But IMDS is the right variable name. So this kind of application opens up. Okay, so it's just, the purpose of this is really to sort of visualize and see all of these images at once. Okay, you can preview it as well, and then you can see more details about that image right here. The path to the image, what the size of the image is. So you notice this is 300 by 300 pixels, fairly small, right? Typically, these slides are much larger. In fact, these days there are high resolution cameras that can do 10K by 10K images as well, right? Like really massive images. And there are ways to work with these images too. Okay, so you see, you can kind of visualize all of these images all together using this kind of an interface here. You can kind of make the thumbnail larger and so on. There are a bunch of options that you can kind of choose to work with this data. Okay, just to generally in any kind of data-driven projects, to first just literally simply see the image, right? See the data. That's very important, right? And so that's kind of what we're doing here. So you can notice that the purple parasite here is kind of like very blobby. It's kind of, there's no simple shape to it, right? You can notice here as well. In this case, it's kind of like a pattern. In this case, it's circular. In this case, it's circular too, right? Maybe this is a parasite, maybe it's not, right? Excuse me. So this is useful to see as well, right? Cool. So that's the first step of just looking at visualizing and accessing data that you have on your computer, right? There are several ways of doing it, and we sort of walk through a few of them, right? Now let's look at the second step here, where and this is the personally for me, and I'm hoping for most of you, sort of the interesting part of prototyping these algorithms, right? I just noticed a question about what database is this, right? So this is this data comes from the CDC, the Centers for Disease Control, and this particular website, the link here can point you to where the images come from. Okay, so this is not a large-scale data set per se. It's only 16 images. We are using this as a sort of a demonstration to sort of look at a bunch of images like this. Okay, clearly there are many other data sets out there where there might be a larger set of images as well. Okay, so hopefully that answers the question. Please keep questions coming, and I'm hopeful that we'll be able to answer as many of them as possible. If I cannot, I'll get back to you via email. Okay, all right. So the second step here is the sort of algorithm development to try to find out how we can analyze this image and this data, right? To find out the parasite infected cells as well. Okay, so we this section has no code, if you notice, right? So all of this is just text. So when I press this button here, nothing happens because there's no code, right? Nothing runs, right? So how do we tackle a problem like this, right? The first kind of pass of an algorithm to do to analyze this would be to do something like this right here. Okay, so you see this background region here outside the cell area is black here, right? So that's because we are doing this thing called thresholding on this image. Okay, so let me show you this image again. The background here gives us no information, right? There is no just by looking at the background here, you can't make out how many cells there are. Maybe you can by looking at the holes in the background, but you definitely can't make out how many cells are infected, right? So this is not very useful information for us to work off of, right? And for that reason, we are not going to make use of this background, and we'll segment it, right? So segmentation is this the process by which you divide your image into certain sets of regions. Okay, in this case, by thresholding, what we are attempting to do is we're saying I don't care about the background, right? So I'm going to remove them, and then I can focus only on the cell parts which are interesting, and then I'll focus even more on the ones that are infected. Okay, so that's what we're going to do here, right? How do we do this? So there is this application or app in MATLAB called the Color Thresholder app. Okay, so let me open this and show you how it looks and how you can work with it. Okay, so this is the Color Thresholder app. Okay, I opened it by clicking this link, which essentially what it does is it runs this color thresholder in parenthesis target image. It runs this code in MATLAB just by pressing this link, right? An alternative way to open the app is to go to this app section here. So home, plots, apps, the third one. And then depending on what toolboxes you have installed, you should be able to see a bunch of apps. Okay, so I see a bunch of these image and vision apps here. The color thresholder is also listed right here. Okay, so that's how I open the app. And so here is my app. Now, the first thing that comes up here is this thing called choose a color space, right? So you may or may not be familiar with the theory of color spaces, but this image is something has color channels, right? It it could be RGB, right, which is red, green, and blue. That's how it's kind of organized in the file itself. But you can also convert this image into other color channels as well, right? So HSV stands for hue, saturation, and variance. YCBCR is this other, I don't exactly know the full form off the top of my head, but this is another color space where you have the blue and the red colors are kind of pulled out in some way, and then you have the luminance, I believe, in Y, right, or the brightness in Y. LAB is another color space. So what you're trying to do here is really this background region. You want to try to sort of separate it out, right? So you're trying to, this is the color cloud associated with that color space. Okay, so, and you can rotate it and see how it looks. And you'll notice that the elements here are or the dots here correspond to all the pixel values here. Okay, so each pixel here happens to be a dot in this color space. Okay, so if you look at RGB, for example, the white regions are somewhere, I guess, in the middle, right? Or in this corner of this blob, but somewhere in the middle of this entire cube. And so the idea is I want to be able to draw a line in this 3D space to divide this white region, the background region, from the rest of the points here. Okay, so to find the kind of color space that lets you do that easily. Okay, so I'm going to choose RGB, for example, just to show you how it works, and then you'll see something like this. Okay, so the same color cloud is here, and you can sort of rotate it and see how it looks like. And then you have these sort of horizontal bars. Okay, so let me show you very quickly and how easily you can do this, right? You may know already, or you may not, but 0 is sort of like indicating dark for the red channel, and 255, because this is uint 8, right? Unsigned integer 8, 8-bit, is extremely bright, is the brightest possible red, right? The same thing for green and blue. So if I can sort of slide this, notice what happens, right? So there's immediate, you can sort of figure out what's happening here. I am excluding the most brightest red pixels, and then finding out what the output looks like. Okay, you can change the opacity of the background and sort of see what's happening. I'll change the color as well, so that maybe I'll make it blue, and you can see what the segmentation is doing while we make these modifications here, right? When I remove this, when I go through this part of the region where there are lots of red pixels, I actually also like remove the cell regions as well, right? I don't want to do that. I want to be in between this, so that if you notice, the background is removed, but the cell regions are still active, right? You can look at the binary version of this as well and see what this means, right? How this looks. You can do the same thing for green as well, and sort of clean it up a little more, right? You can do the same for blue as well. Blue is a little more sort of noisy at the high pixel values. This is a histogram, by the way, if you didn't already notice. So I can sort of clean it up a little more, and you'll also notice here in the color cloud that the white regions are gone, right? And I can sort of clean this up a little more, and you'll notice that the other regions go away as well, right? So this is you can hide and show point cloud just so that you want to see this more clearly. So this is a very easy interactive way to segment your image based on color. Okay, that's why it's called the color thresholder, right? You could choose a different color space. Let's say I'll just quickly show you the Hsv color space, and it looks slightly different, but you may be able to appreciate this as well. So okay, I was showing binary, and that's why it was all white. So you can kind of do this here, where you can threshold in the hue domain. You can threshold in the saturation domain right here, or you can threshold in the V, the hue saturation variance domain as well, and you see what happens here, right? So maybe there are other ways, possibly better than RGB, that you can experiment with over here, right? Once you're done with this, you can then finally say export either only the images, or the cool part is you can export a function, right? So when I click the export function button, everything that you did graphically, right? Converting the color space, defining these threshold, those boundaries, and then creating the mask, right? There is code generated. So this was auto-generated right now by this app, right? So you don't have to write this. It is auto-generated by the app, okay? And so that's really cool, I think, where you don't have to manually do this on your own. You kind of interactively play with this data and then just say generate export function, right? So that's a very interesting and from a engineering student perspective, I think this kind of analysis is great, right? So I spent quite a bit of time here, so I'll go through this more quickly going forward. So hopefully you understand what's happening. We're removing the background here, right? And so we've created this function here through this app already called create cell mask. Okay. So what happens is the input to this is just the original image right here. The target image is what we call it. Let me zoom in so that you can see it a little more clearly. And the output is this thing called cell mask. And then we're just displaying both of them here. Okay. So essentially, if I run it, it's just going to do the same thing. I've changed the target image, so you see this other different image here. So you see what's happening, right? We've removed the background here and made it easier for us to work with just the cell regions only. Okay. So there's a question I see. Thresholding is image sensitive based on resolution. Yes. In case different samples are of different resolutions, we need to pre-process the image. Right. So there's a slight nuance. So the thresholding is only based on the color, right? Whether this is 300 by 300, 500 by 500, 10K by 10K, we only look at the color of each pixel. So the resolution from that perspective doesn't matter. It's not sensitive to resolution. However, if you have the resolution part comes in where you want to see the edges of these objects, right? If it's not high res enough, the edges might be jagged. It may not really get the right amount of detail that you want, right? You may not be able to even see these specific blobs here if the resolution is too low, in which case you may want to look at images of higher resolution. But the process of color thresholding is still the same, irrespective of what the resolution of the image is. Okay, higher the resolution, the better it is. In this case, 300 by 300 for demonstration is sufficient, but typically the image sizes are larger, right? So hopefully that answers the question. Thank you very much, and please keep questions coming. This way, it's more interactive, right? Right. So we're just running this, and you see what we've done here. We've removed the background. Okay. The next thing after removing the background is we want to look at only the important or the large regions. Okay. And that's what we'll do next, where you notice these holes here, we may not want to keep them. This hole here, for example, came in erroneously, right? This one here, for example. We'll try to clean that up as well. Okay. Let me actually, to keep things consistent, go back to this image. I believe it is the fourth image. And so, the images that you'll see later on will correspond exactly to what you see here. And that way you won't get confused, right? But you can do this for other images as well. I will just keep it consistent so that everything's all right, okay, for now. Okay, so now let's look at the region analyzer app. So this is another application that helps you sort of select these regions more easily. Okay, so what we're doing is we have this cell mask right here, right? So the white regions here are the regions that we're interested in. The black portions here are sort of the background that we don't want to look at over here, right? The other thing that you may notice here is this table of data for certain regions. Okay, so let me show you what happens when I, let's say, select this 9th region. Okay, I click on here, and you'll notice that it selects this or it highlights this. Okay, so what this means is this 9th row corresponds to this particular blob, and the area in pixels of this blob is 3129. Okay, so there are 3129 pixels in this area. The major axis length, if you're looking at the properties, right? If you can fit an ellipse on this, so the major axis length is 64, minor axis is 61, so it's not exactly circular. It's a little, eccentric, slightly eccentric, not very much. You'll notice, for example, this one is even more eccentric, right? It's 60 in one and 39 in another. Let me try to find one that's far more eccentric. Maybe this one. You see, it's in the corner, so it looks more like it's longer vertically than horizontally, right? And that's reflected by this axis length. In fact, you have eccentricity values as well, right? That can give you an indication of what the shape is. You get perimeter, equivalent diameter, orientation, and so on. All of these are properties of each of these objects. Okay, so let's sort them by area. Okay, and so now we see that this is the largest contiguous blob. This is the smallest one right here. I can't even see where it is. I think it's this one, a very small 2-pixel region here, right? And these are other regions of interest as well. Okay, so what we want to do now is we want to remove regions that are very small, like this particular noisy kind of region here, right? So you can then filter this by any of these properties. Okay, so let's say what we'll do here is we'll say we want only the large regions. Okay, so I'll say I want minimum pixel size should be 500. What just happened here? Let me go to filter and then say in for infinity, right? And so already the regions that are less than 500 are not even shown, right? So I'll go back and make this 0, and then you'll see all these other smaller regions, right? Now I'll make it 500, and then you'll see only the large regions are here, right? So I've removed this noisy area here. Okay, so that's the kind of processing you can do next to clean up your data here. Okay, so to focus only on cells that are large enough. Okay, so you can do this here as well, and then finally also export function in this case too. Okay, so when I click this, you'll notice that you get this filter regions function created, auto-generated for you. And then you can do this kind of analysis, exactly what we did right here, to clean up the data as well. Okay, again, graphically, you don't have to write any code. The code is written for you, right? So I'm not going to save this. We have already written something like this called filter cell regions. If you want to look at what this contains, you can right click and then say open filter cell regions. And this is the code right here. You'll also notice that we've filtered out by area, and we've chosen only 500 and above here. Okay, so even once you've created the function, if you want to really understand what it does, you can just read through the code, and then you'll make out what's happening. Okay, so that's what is done here. And then if you notice the differences between this image and this one, you'll see that these small kind of regions here, they go away, right? So in fact, the holes here are also gone, right? So you can sort of filter your data and clean it up a little more by doing this kind of a process. So when I run this, it'll just show the same thing again, because same function, and so it's easier to handle and get a cleaner image like this. Okay. All right, so that's another level of processing. You can also look at the properties here of the pixels. This is the largest region. This is the smallest region. The same thing that the app was showing. The function can also return right here. Okay, so this is the next step of actually just focusing only on the cell regions here, right? Now we want to do something slightly more involved here, right? So I'd like to draw your attention to this 3-cell kind of region here, right? So there are 3 overlapping cells and you can see it right here, right? So there are 3 overlapping cells in this thin smear, and once we've cleaned it up, it kind of looks like a single blob, right? So how do we separate them out, right? Clearly there are 3 cells here, but it looks like there's only one when you do this processing, right? What do we do about that, right? So to work around that kind of an issue, we can do this thing called edge detection, okay? So you may notice, and I'll go back here, you may notice that visually we can see kind of an edge kind of region here, right? You can see this boundary visually as humans that in fact there are 3 cells here, and there's an edge here that corresponds to its boundaries. We've lost that information here, but we'll try to regain that back. Okay, the way to regain that is by doing this thing called edge detection. Okay, there are applications to do this as well. Not part of MATLAB. You'll have to download them from this thing called File Exchange. I won't do that here in the interest of time, but there are ways to do this also. Okay. What we've done here instead, and there's no generated code right here. Everything is what we have handwritten over here. We are going to convert this image, target image, into grayscale. Okay, so another color conversion method is to get rid of the RGB, the color channel, and only focus on the gray image, right? We then run edge detection right here, and then we overlay the edge that has been captured as a green color overlay like shown here, and then we just display this image using IMShow or IMShow. Okay, so that's what's done here, and then you'll notice that for this region here we've detected these edges. Okay, so we can make use of this now to separate out these cells. Okay, here too, in fact, if you notice, there are 2 cells. We don't know if they're treated as separate. They are already treated as separate, so we are good there. But hypothetically, if they were not, you could make use of these edges here and separate them out as well. Okay, so that's really the utility of doing this kind of an analysis by detecting edges from your images, right? So the other thing that you may notice here also in this image right here is originally, I'll go back to this one just to demonstrate this. And let me zoom in a little more so that it's clearer. Notice that the edges are not continuous, right? They kind of stop. This line stops here and does not connect to this border here, and we want to make it continuous, right? We want to sort of complete out that kind of connected boundary here, right? And to do that, there are these operations called morphological operations, right? So if some of these terms are alien and are not easy to understand or intuitive at all, please look up these links right here. All of these are documentation links, and I'm hopeful that if you find this interesting, you'll take up an image processing course in your next semester or whenever next it's offered, and hopefully you learn all of these concepts as well. Okay, so this one is called morphological image processing or morphological operations, where you can do these things called dilation and erosion. These are the basic operations, out of which you can compose other operations like closing and opening. Okay, so for example, opening is erosion followed by dilation. Okay, closing is dilation followed by erosion, right? And once you do that, you'll also have to set up this thing called a structuring element. We're just setting up a disk structuring element. Okay, and for more details, we can talk about this if you have questions during the Q&A section. But essentially, what happens is you can sort of make these edges more prominent, right? By by dilating and then eroding, essentially by closing, right? So we dilate and then erode, We could have just closed it or used IM close, but we're showing how you can do it separately as well. Okay, by doing that, you get something like this, and that can help you. This is the original edge image, if you notice, right? And by doing that, you can sort of see these boundaries are now connected. Okay, and that way you can then more clearly sort of separate out these areas. Okay, so that's what's happening here. Is we are saying we'll combine the results of this edge detection with the previous mask that we've got. Okay, so focus on this region here. Notice that the boundaries are now more, you know, the black regions here are connected, right? Which means that you can separate out this blob from this blob here. Okay, so that's what is done there, and that way you can now say that, okay, so there are indeed 3 cells, 3 blood cells in this region, right? So that's the process we're doing here. Okay, right, so we've done all of this analysis, and we are sort of inching closer and closer towards getting these individual cells out, right? You'll also notice that because of our thresholding operation, these regions here are, you know, the parasitic regions here are taken out in some way, right? And we'll work on that next. But really, there's a lot of processing that has already happened. We've removed the background. We've made the boundaries clearer so that we can count the number of cells here more accurately, right? And next, we'll look at actually saying or finding out which ones have these parasitic infections and which ones do not. Okay. So hopefully, so far, everything's so good. I know it's 11:28. We've almost run out of time, but I'll hopefully, if I can take a few more minutes, I can talk about the next few steps. Okay. So the next step is to sort of put all of these things together, right? All of this analysis together. We've, you know, tied everything together in this single function called refined mask, right? So create cell mask was created by the thresholder app. Filter cell regions was created by the region analyzer app, and then we did this sort of cleaning up using edge detection here. We've sort of packaged it into a single function. Okay, then what we can do is we can open this other app called the batch processor app. Okay, and let me open it up quickly, where the idea is you can load a bunch of images, right? You can load images from a folder. So I'm going to go back here. I'm going to choose this folder and load the images. And then you'll see all of them listed here. You can specify a batch function, right? And then you can open, and I'm going to go into code and choose refined mask. Okay, so I specify this function. And now I can run that function on all of these images. Okay, so I just press the process selected function, and then if you notice, there is a results tab here, which kind of shows, right? So you can see the original image and the processed image, and you can see this for each image that, you know, we can either process selected or process all. And if you process all, you'll see these green check marks for all of these, and you'll see the same process applied to all of these images, right? And immediately you may notice, for example, on this one here, that our sort of algorithm has kind of failed here, right? So, you know, we see these edges here, but really they have not been detected as edges in our output image, right? Which means that our algorithm has done a good job potentially on this 4th image. So this is what we prototyped it on, but has not generalized or cannot work on these other images here, right? Maybe what happens when the background's different, right? So you see, we've also lost some of the cell regions also, right? Because our color thresholding maybe was not, we didn't try it while prototyping on this kind of a background image, right? So we need to do a lot more work to generalize, okay? but hopefully you understand and you appreciate the need for sort of ideating and prototyping your algorithm on one image first, and then also quickly finding out if it works for others, and then adapting based on what's happened here. Okay, so in this one it looks like the parasite is out by itself, but we've lost that information here, right? So what do we do in that case, right? So I'll close the app and I'll whoops. It says unexported results. I'll say yes. I don't care about that. So let's see how to handle that. Okay. So now we want to fine tune this algorithm, and particularly we want to improve the segmentation so that we see the boundaries better. Okay. In the interest of time, I won't go into a lot of detail here. I'll share this with you and you can explore this further. There is this other algorithm called watershed. Okay. Which is a better segmentation algorithm. And essentially what happens when you do this is, the algorithm tries to divide regions based on the intensities. Okay. And it's called watershed because it's almost like, if you think of the intensities as hills and valleys on your color sort of domain, right? It tries to sort of find these catchment basins or watershed regions, and then tries to segment it that way. Okay, so the function name is watershed, and when you do this segmentation here, it kind of divides the regions into these sort of blobs here. Okay, so that's what's happening here. We have overlaid this kind of boundaries of these watersheds by using this right here. Okay, so double equal to 0 of the output of watershed. Okay, so this is a advancement and another algorithm you can try, knowing that it didn't work on this kind of grayscale kind of washed out slide, right? You can then improve this by use this calculation to improve. So we are not doing the edge detection anymore. We do these two parts and then we do this watershed part, and then you'll see how this looks like. Okay, so this is slightly better now, right? So you can still see the boundaries here if you notice, but the rest of the processing is kind of maintained. Okay, so this is another alternative method to do this segmentation. You'll also notice that it also tracks, or it also catches these regions of other colors here as well. Okay, and that's useful for us too, because we can use that information to say, okay, there is a parasitic infection in these cells here. This cell is clean visually and clean here as well. So that's good information that we can work off of as well. Okay, so that's about watershed. The other thing you can attempt to do, and I won't go into this again in the interest of time. I can take this maybe if there are questions about it. You can try to detect circles. Okay, so fortunately for us in this case, most cells are close to circular. We saw the eccentricity earlier, and we found out that they're not exactly circular all the time, and that will be a wonder if all cells are exactly circular. But you could hypothetically approximate these blobs as circular and try to detect circles as well. Okay, so there's another app here called the image segmenter app, which can help you find circles, right? And then you can specify the diameter range, and that way you can only detect circles of sizes that you care about. Okay, and that might be another, and when I run this, you'll see here as well that you can sort of detect these cells by detecting circles and then do analysis beyond that. And notice how nicely it's sort of detected these two and then kind of found the intersection as well here, right? Now quality. Now there's also variations in quality which we have been alluding to a fair bit. Number 4 versus number 13 particularly. Look at how different they are, right? We have to account for that. So we need a very robust algorithm. One way to account for this difference is to get rid of the color information, right? We'll also lose information about the parasite here, which we'll take into account, but the rest of the color information, just because this is pink and this is gray, that doesn't give us any information, right? So you can get rid of that by doing this thing called IM binarize, meaning you're binarizing the image. There are methods called Otsu's thresholding method, which is very popular and also included in most image processing courses, which can help you do this. There's also histogram matching, right? Which matches the histogram of your target image to a reference image, right? That way you can homogenize the data set. So when I run this, you'll see the after histogram matching, right? So this is the original image. We've matched it with the histogram of this image, right? And so you can see the colors are now more similar, right? So we've not lost the parasite infestation data or details here, but we've sort of matched the color more to this sort of target or reference image right here. Okay, so those are other methods that you can employ as well, right? Now, finally, with all of these methods put together, we've sort of tried to, create one single function. It's called the detection mask function. Okay, so we read an image here, for example, as the target image, which we are going to use to match the histogram of this input image right here. Okay, then we use the circle segmentation. We then initialize some variables, and for each region that we, for each circle that we find, we do some kind of analysis here. And you can read through this in more detail. Essentially, this is the same kind of analysis where we do the filtering by area. We then, find we OR a couple of images and find out if they're infected and so on. So I'll let you read this in more detail later if you're interested. We've put all of that together by making use of these new refinements into this detection mask function, right? And now we can finally run that detection mask function on all the images using the batch processor app again. Okay, so I'm going to load all of the images again over here. So these are the 16 images. I'll then also select the detection mask function that sort of combines everything together. Okay, so I'll open this, and now I'll process everything at once, and then you'll see what happens. Okay, and I'll show the results as well. You'll notice that this is how how it works, where we've also highlighted these regions where the infections exist. Okay, so we haven't gone into the details of how this highlighting was done, but we actually looked at how these circles were detected, and the green overlay is just visualization, right? There's nothing, there's no processing that's happening really for the green ones. It's only that whichever of these cells have these red regions that we've identified based off of the the ORing of that image that I mentioned right here, right? So this is where you kind of detect if the cell is infected. Okay, so with that, we've kind of identified these cells. We've also identified the other cells here too, through these circles, and that way we can make this assessment going forward. Okay, so again, very quickly, if I can scroll down and show you how this looks like for all the images. I'm just going to run this again, and you'll see that we can generate results like this, where we can then make this estimation of, there are 12 cells here, only 2 of them are infected. So now the infection percentage is 17%, right? This one has much more infection. It's 44%, 7 out of 16, right? And so on. This one's very, only 1 cell is infected here, right? So that's kind of, the process of analyzing this kind of data. Okay. So that's really it. I really wanted to walk you through this single example. I know we've spent a lot of details or time in nuances and details, but hopefully that's useful for you to sort of keep in mind. I'll be happy to share this script with you, and you can run this on your own, make changes to this analysis, and find out, if you can do this faster or do this more accurately if we've missed out on something, right? So please feel free to work with this and experiment with this on your own. But hopefully, let me go back to the one slide that I had. Sort of as a summary, we sort of went through accessing and visualizing data. We went through prototyping very quickly using applications. We then tried to automate it to run using the batch processor application on multiple images. We found out that the algorithm that we came up with initially was not good enough, right? Did not work for images with slightly different color profiles. So then we fine-tuned it. We attempted watershed. We then said, okay, we want to do histogram matching. And so we sort of matched the color profile of all the images to one reference image. We then thought, okay, we counted for image quality and variability by doing that, right? By histogram matching. And then finally, we put it all together in one function and ran it on the entire data set of 16 images. And then we could sort of make estimates based off of that, right? So that's really all. I'm sorry I went 10 minutes over, I think, but 12 minutes over, so apologies. But hopefully this was the extra time we spent was useful for you to understand the topics in more detail. Okay, that's it really, based off of the file that I had, the live script that I had. That's all that I really wanted to show. I'm open for questions now for the next about 15 minutes. And if you have any clarifications that you'd like me to make, I'll be happy to make them now. Thank you for your time and attention. I'll pass it on to I believe Professor Chaitra, is that right? I'll pass it on to you to take on questions if there are, or if I can clarify anything, I'll be happy to do that.
Yeah, thank you, sir. It was a wonderful and informative session. Thank you, sir, for sharing your knowledge. We will now move on to the question and answer session. I request Ms. Nandini Maninarayana to put forth the questions.
Amit sir, I have a couple of questions here.
Yes, Professor.
My first question is, how can I segregate these samples based on high, high, low, low, high, and low, low?
I don't know if I understood the question right, Professor.
Yeah, yes, sir. I'll clarify that.
Yes.
How can I segregate the sample images based on their resolution? Sometimes images will be like background is in high resolution and detecting object is in high resolution. Similarly, in case of background is high resolution and sometimes detection object is low resolution.
Right. So if I understand right, I guess what you're saying is, and this is a contrived kind of example where all the images are of a certain size and certain resolution, right? So all of these images are in fact 300 by 300. What if there were images of different resolutions? How can you account for that, and how can you kind
segregate?
Of separate them out, right? Yes. So if I understand right, then one way to if you have the resolution data, right, meaning if you know the size of the images, you can simply threshold it, right? What I mean is, this image is 300 by 300, right? This last one, let's say, is 3000 by 3000. So any image that's less than 1000 by 1000, I'll separate it as low resolution. Anything that's greater than 1000 by 1000 resolution, and so you divide your data based off of just that metadata of the size of your cell, right? You don't need to do any image processing to do that, right? So that's one way.
Sir, with respect to the same question, how many samples I should consider in each category, sir?
Right. So that's a great question. So really, what we're doing here again is this is just a demonstration, right? So 16 samples here, and this is also, if you notice, this is a binary classification problem, right? So it's is the cell infected or not? So there are only two categories of outputs here, and so how many images are necessary? In the medical space, it so happens that there is so much variability that you can see here as well, right? That as much data as you have to work with and validate your algorithm, the better it is. However, there are limitations, right? So clearly, if you're looking at cells, cell slide images like these, maybe it's not that difficult to get a few more images. But if you're looking at cancer detection, for example, right, there's only a limited set of data that you can get access to, right? The simple answer to that question is get as much data, as many samples as you can, because again, the accuracy here is the demand for higher accuracy is more important in medical situations than otherwise, right? We don't want to come up with erroneous results. Erroneous results are relatively more tolerable in autonomous driving, where there's a human behind the wheel also who can correct if something goes wrong. But in this case, we do not want to give wrong inferences to a doctor. So given the performance requirements and the variability in the data, I'd say as many images as possible. And in this case, it could be quite a lot. But in certain other situations, you may not be able to get that much data, right? So that's a consideration to keep in mind too. Hopefully that answers your question. I hope I wasn't rambling.
Yes, sir. Sir, my second question.
Yes.
India is low-income country. Right. In order to reduce overall cost of automated detect system, can we use mobile clicked images as a samples?
That's an interesting question. So clearly, for applications like this, right, you would need specialized instruments. And so for this specific situation, that may not be an option, obviously, right? There may be other medical image applications or medical image kind of situations where you could do that potentially, right? So for example, let me broaden that a little more to the current situation, right? For the coronavirus situation, we are aware of several labs all around the world using their own devices, their own mobile phones, to record their breathing and their audio speech samples, right? And they use that as the sensor or the data source for collecting information about people who either have been infected by the novel coronavirus or people who have not, right? So in a low cost kind of setting where hopefully most people have mobile phones that can record either pictures. I can't think off the top of my head of an example of what kind of pictures you can. Maybe there are dermatological applications where you can take pictures of skin issues. I'm not aware of them, to be honest, and hence I'm taking the example that I'm aware of audio, right? Medical audio data, which you can collect through your cell phones. And so they're doing this, and they're collecting thousands of samples. In fact, I think at this point in time, this one group that we are talking to, they have three weeks worth of data, is what they mentioned, right? And this is collected by all of us, like you and I can do this tomorrow as well, right? And then you can run these kind of machine learning algorithms. Some of this analysis, like thresholding, segmentation, all of these can also be adjusted or applied to one-dimensional signals as well. So we showed this in 2D for images, but you can do this for 1D data as well, right? So people are working on this kind of crowdsourced data based analyses, right? And that's something that I think there's a lot of scope for going forward as well. From the image side, I am not entirely familiar with applications where you can use your own devices to collect data like this. Clearly, definitely not this kind of pathological data. Clearly needs microscopes and specialized equipment. But there may be other applications that I may not be aware of where you can do that for images as well. So hopefully that helps.
Sir, my next question. Yeah. To determine the severity of the disease, how many different slides of the image are required per patient, sir?
That is a question I am not qualified to answer. I wish I knew the answer. I do not. What we're doing here in this case is we can only give an estimate of the number of infected cells on this particular slide, right? The question you're asking will allude to things like, let's say you take 10 slides from the same subject, right? And then maybe one slide has 40% infection, infection rate here. Another one has 20. Maybe you have a sort of a lot of variability there, right? How do you kind of combine that and put that together to provide a single estimate to more accurately represent the amount of infection there is in this patient or in this subject? I'm sure there are statistical methods to sort of combine all of this data into, maybe the mean is a good measure, right? Maybe the worst or the highest infection rate recorded by any one of these slides, maybe that's a good measure, right? However, these are only indicative, meaning they're not definitive results. And that's kind of why I said, these methods are not meant to replace physicians and doctors. They are only meant to support and provide more stronger data-driven evidence. It's kind of like if you have a fever, this is going to tell you what your temperature is to some extent, right? It's going to estimate your temperature for you. It may not even be able to tell you the exact temperature. It will estimate the temperature, but then you still need a doctor to say, okay, you know what, based on my understanding of this diagnostic, I believe this is the next thing to do, right? So that's a caveat I want to highlight and mention. that this is just an assistive, supportive technology that you could build. In no way is it a replacement to a doctor, and it's not definitive in that way. And to come up with a aggregate single metric, that will need a little more work, which I personally am not qualified to answer. So hopefully that helps.
Sir, what is the normal size of the input image we need to consider in the automated detection system?
Right. So that's a great question as well, Professor. Again, for the demonstration here, we've only used small 300 by 300 slices. Let me show you this thing. Let me try to bring it up quickly on my screen. It's called the big image. Sorry, let me just. To answer your question, really, pathological slides are, there are really large resolutions and very large slides as well, right?
Yes, sir.
So let me try to bring this up very quickly. I'm trying to figure out. Yeah, so let me show this here, and this might give you some kind of an understanding. So this one here is yeah. So let me zoom in here. So there's this data set for it's called the Chameleon Dataset, and if you notice, the image is multi-resolution, has 8 resolution levels, and the finest level is this resolution here, right? It's 50K by 60K. So this is far larger than your the latest TV resolutions are 4K and all of that, right? This is 50K by 60K. So depending on the kind of applications you're working on, you may need to go to this level of resolution. Okay, for this particular application, given that in terms of number of pixels, even with 300 by 300 pixels, we could sort of make out the parasitic infected regions here. That may be sufficient, right? Again, it also depends on what the actual physical resolution of the slide is. I'm not entirely aware of the actual numbers. I'd imagine the CDC website here would have that information. So if I can just quickly go here and try to find out, there is likely more information about the data set right here. So you can find details, hopefully, somewhere over here. I don't know what the actual in millimeters or in micrometers, what the resolution is. But pixel wise, it can go all the way up to, like I indicated here, can go up to 50K by 60K and so on, even larger, in fact. So depending on the application, the higher the resolution is, the better it is. For this one, it's a demonstration, so it works. But in other cases, you may have to go up to this level.
Thank you, sir. That's all from my side, sir.
Great. Thank you for the great questions. I really appreciate your efforts and attention in asking these questions. So that's about it. I think I can take more questions. I'll just post this up very quickly. So this is my email address. I'll just put it in the slideshow mode. It's akamath@mathworks.com. So any questions you have about this that you were not able to ask right now, please feel free to email me, and I'll be happy to respond as quickly as possible. Also, there's a feedback link I see in the chat window, so please do consider posting your feedback, and I'll be happy to hear how I can improve and how we can make this more useful for you. Well, that's about it from my side. Thank you very much. I'll pass it on to Professor Sharma for the final words.
Yes, sir. Sir, I thank the management for providing me an opportunity to host the webinar. It's my privilege to acknowledge our beloved HOD, Dr. Dayakshini, for providing constant guidance in organizing the webinar. My sincere gratitude to Mr. Amith Kamath from MathWorks for the brainstorming session. I am grateful to all the organizing committee members for their support. Finally, I thank all the participants for their enthusiastic participation. Thank you, one and all.
Thank you, ma'am. We have come to the end of this session. Thank you, one and all. Have a nice day.